This scenery, with its vast areas of rock outcrop and bare sands, is magnificent in its starkness. It takes little imagination to see why the inhabitants of this barren land, Jordan, find life difficult. Their essential need is for water. The starting point in any water story is the amount of precipitation. How much water vapor, originally picked up by the air passing over the oceans, falls as rain or snow, most abundantly on high ground. Now, Jordan is near the eastern extremity of the Mediterranean, and although the textbooks tell us that the Mediterranean experiences warm, wet westerly winds in winter, this is progressively less true the further east you go. During Jordan's winter, winds come from all directions, and only those coming directly from the west carry significant amounts of water vapor. So, rainfall is primarily in winter, is spasmodic and unreliable, and falls mainly on the high ground, on the eastern Rift Highlands, and importantly, on highland areas such as Jebel Druze, to the north of Jordan, in Syria. Let's examine what happens to the water that falls on the eastern Rift Highlands. We'll take an east-west geological cross-section through Jordan at the same latitude as the Dead Sea. Rain and snow falling on this highland area in winter will either move away as surface runoff in streams that lead to the Jordan River, or percolate through the near-surface rocks, moving sideways along permeable sandstone units that lie on top of impermeable igneous rocks. These near-vertical cliffs are the permeable sandstones, and the darker, gentler slopes at their base are 600-million-year-old granites, impermeable igneous rocks. The boundary between the two is a nonconformity. The nomadic Bedouin who spend their lives in areas like Wadi Rum in southern Jordan know that only where there is vegetation is there any chance of water. So water is here. But why? Sandy Smith.
This well is formed by water that's been infiltrating through this permeable sandstone. It's stopped by this impermeable granite beneath me and forms in a hole in the granite. And this water in this well is used for watering crops, for animals and for people. And the first people who settled in this area, which were the Nabatean Arabs about 2,000 years ago, used wells like this. But the centre of their civilization was about 100 kilometres to the north of here, the city of Petra. This ancient city is some 2,000 years old, and about 25,000 people lived here. The water supplies came from outside the city, and even today, those systems where water was stored are still used. In 106 AD, the Romans laid siege to the city and cut off the channels which supplied Petra's water. It was only a matter of time before the city fell. It is in these desert countries that the necessity of water to man is forcefully brought home. All of our other resources make life more comfortable, more efficient, but without water we die. The Nabatean Arabs extended throughout much of Arabia, and this rock is the same rock as at Petra. It's even got the same brilliant colours we saw at Petra. It's called the Nubian sandstone. It's deposited by rivers, and the same rock extends not only throughout a lot of Jordan, also through a lot of Arabia and much of North Africa. But below it is the oldest rock in Jordan. This is a granite. It's Precambrian and it's impermeable to water. And before the Nubian sandstone was deposited on it, it was eroded flat. So the Nubian sandstone unconformably overlies the granite. Here's the unconformity. So in Wadi Rum, the vegetation traces out the unconformity. Elsewhere, its position is easily identifiable, but wells only occur where there is vegetation, and these are at widely spaced intervals. But what about other parts of Jordan? Ian Gass.
This is typical Jordanian desert. No vegetation, which in turn means that there's no water at or near the surface. Indeed, the annual rainfall here is less than 50 millimeters. But there are places where water does come to the surface and we get oases, such as this one at Azraq. Here, immediately behind the oasis, is the front of a lava flow. And it seems quite possible that the oasis is here because of this lava. Seemingly, we have a paradox, for igneous rocks are usually impermeable, yet there's no doubt that this water did not fall here. To discover how the water has been brought here, we must examine the anatomy of a volcano. As lava flows, its surface cools, forming a hard, rocky surface. This, in turn, spills over the front of the flow because the top of the flow is moving faster than its base. So, as it advances, the lava flows over its own surface debris. Any cross-section through a lava volcano will show solid lava centers separated by rubbly horizons. No water is going to move along this massive flow center, but outcrops of this flow's base show its blocky nature. Blocks of lava, originally formed on the lava surface, are now below its massive center. So this is the kind of rubbly zone along which water would move quite easily. And there's another interesting point here. There's a break here, the rubbly zone above, and this rather redder zone beneath it. That's the weathered top of the underlying flow. So the weathered top of this flow, the rubbly bottom of that one, is a beautiful channel for water to move along. Azraq's water starts off as rain and snow falling on the higher slopes of Jebel Edruz in southern Syria. A similar system exists further south, where precipitation on high ground to the west of El Jafar percolates eastwards towards the inland basin through near-surface rocks. During a recent Jordanian government United Nations project, numerous wells were sunk in this area to tap the near-surface water, and this is used primarily for irrigation in the El Jafar area. The Bedouin have long known that water existed just below the surface here at El Jafra, and they dug shallow wells to get the water for their stock. The problem here is that because rainfall is low, not much new water is coming into the system. The water that is here is pumped, used for agricultural purposes. It then percolates back into the ground, there to be pumped once again to the surface. It is essentially a closed system, and the problem is that every time the water is recycled, its salt content increases, so that in 10 to 20 years' time, all the water here at El Jafar will be too saline for agricultural purposes.
Nomads rely on oases, and in parts of Jordan, water rises to the surface quite naturally. This artesian water emerges from confined aquifers. It doesn't require pumping. There are a number of confined aquifers in Jordan, recharged mainly in the eastern highland areas. The infiltration of water into permeable rocks maintains a store of groundwater, which is prevented from reaching the surface by an overlying layer of impermeable rock. The pressure at any point of the aquifer is related to the height of the water table or its theoretical projection, the piezometric surface. In some places, especially away from the recharge area, the piezometric surface may be above ground level. So the water in the aquifer has sufficient pressure to reach the surface if there is a break in the overlying impermeable rock. So if a well is drilled down to the aquifer, water will flow to the surface under pressure. Artesian wells are the simplest way of bringing water to the surface. So far, we've been looking at groundwater, but there are areas of Jordan where surface runoff is important. In the highland area, where rainfall is greater, many of the valleys have surface water flowing in them for part of the year, and are known as wadis. One such valley is Wadi Wala. High in the wadi, there is very little vegetation growing on the wadi sides, so soil and bare rock are easily eroded by surface runoff. The sediment is carried down the wadi and deposited, forming areas of fertile soil, potentially very suitable for growing crops, as long as they receive enough water. But rain is very irregular. When the rains come in winter, there is a high surface runoff. Water also infiltrates into the ground, where it contributes to the groundwater stored in the permeable rock. If the water table is higher than the wadi floor, the groundwater can also supply water to the wadi by base flow. So the combined discharge of groundwater and surface runoff produce a river flowing in the wadi floor. When the winter rains finish, there is no longer any surface runoff, but the river still flows, fed by base flow from the stored groundwater. However, with no recharge, the water table gradually falls until it is below the level of the wadi bed, and the discharge from base flow stops. We're quite high in Wadi Wala, and although this rock surrounding the place is a good aquifer, there's no water discharging from that aquifer into the wadi bed as base flow, simply because the water table is below the surface of the wadi bed. There's no base flow and there's no surface runoff, so from now and throughout the summer months, the wadi here will remain dry. However, further downhill, the wadi may intersect the water table again. We've come 10 kilometres further down this valley, a bit further along, and there's water flowing here. This can't be surface runoff because there's been no rain in this area. Instead, it's base flow. It's water that's been stored during the winter months in the rocks surrounding the aquifer, surrounding this wadi, and it's been seeping into the wadi bed. And this means that the water table in this area must be above the level of the running water. There's enough water stored in the aquifer to keep this steady base flow going during the summer months. And with this water comes life and settlements in the area. The supply system is simple and effective. And by careful use, there is enough water available, even in the summer, to grow crops successfully. This simple type of irrigation uses surface furrows. But only about 50% of the water is actually used by the crops. The rest infiltrates into the ground through the surface furrows or evaporates. In Wadi Wala, the vast majority of water is available in the winter when crops are not grown, so it flows away unused. By building a reservoir, it would be possible to store this winter runoff and use it in the summer to increase the crop yield. Surface runoff has been stored here, where the lowest part of Wadi Kafrain runs into the Jordan Valley. The reservoir was built in 1968 and can store enough water to irrigate 1,500 hectares of land. It's one of the dams that has been built to irrigate the fertile Jordan Valley. And this reservoir, the King Talal Reservoir, is a major supplier of water for the valley. It can irrigate 6,000 hectares of land, and it traps water from the river Zerka. This storage of water in turn leads to agricultural produce on a commercial scale. The signs of success of the Jordan Valley project are here, in the marketplace of Amman, the capital city of Jordan. All varieties of fruit and vegetables are produced, and much is exported. They go not only to other Middle Eastern countries, but to parts of Europe as well. In the early 1950s, the Jordan Valley Authority was set up to organize an intensive irrigation program. To see how this area became fertile in modern times, we'll examine how this deep valley was formed. The Jordan Valley lies between the Dead Sea in the south and the Sea of Galilee to the north. It was formed in tertiary times, during the Miocene, by about 100 kilometers of left lateral movement along a transcurrent fault, which extended from the Gulf of Aqaba through Jordan into Syria and Lebanon. This movement tilted and sheared off sediment from either side of the fault, forming a deep valley, which is below sea level. The River Jordan flows in a narrow gorge in this valley, and halfway up, the River Zerka flows in from the eastern highlands. And at the north end, the third river in Jordan, the Yarmouk, joins the valley. The Jordan Valley has good soil brought down to it by the rivers and by the side wadi flow, and it has a very warm climate. Even in January, the average temperature is 14 degrees centigrade. So the good soil and warm climate means it's very suitable for agriculture, if only water could be taken to the areas of the valley which are dry. And that's what this canal is doing. It's carrying water along the valley. This is a few kilometres from the north of the valley, at the town of North Shuna. And this canal is flowing 96 kilometres to the south of us, under gravity, almost to the Dead Sea. The canal is lined with concrete to prevent the loss of water by infiltration. It was built along the side of the valley where it is higher than the fields, so water from the canal will flow to the fields under gravity without expensive pumping. Water is supplied to the farmers quite cheaply, much cheaper than the cost of drinking water. But because growing crops need such a large amount of water, farmers have a price incentive to use water most efficiently. Farmers use pumps to produce pressurized water for different types of irrigation. 4 years ago, the farmer planted a few fields with citrus trees, and water is brought to the field through pipes, which stops it being wasted through evaporation and infiltration, and it's spread evenly across the field by the sprinklers. This is called spray irrigation and has an efficiency of water use of about 75%. It may seem a waste to irrigate the ground in between the trees, but this was found to be necessary, as when water was just supplied to around the trees, salts built up in the ground between the trees. And when the rain came in winter, these salts were washed down to the tree roots, and they didn't like it at all. But if water is supplied evenly over the field all the time, this prevents any salt build-up. The most efficient type of irrigation is drip irrigation. These are eggplants, and they're fed with water through a plastic hose laid out across the field. There are holes in this hose at small intervals, and a seedling is planted by each of these holes. So each plant is fed with its own individual drip feed. It gets exactly the right amount of water from this drip, and the plants are also spaced out at the right intervals for eggplants. Very little water is wasted by this, because water is supplied right to the plant roots, whereas in between the rows the earth is completely dry. Nothing is being wasted by evaporation here. This plastic covering around the plants stops water being wasted by evaporation from the soil near the plants, and it also cuts down on weed growth. If these plants were bananas or grapes, they'd be spaced further apart and they'd also have more water supplied to them. The water that's used for agriculture competes with the country's domestic requirement, water for the people. And that's not the only problem in this region. So water is being used in the Jordan Valley for irrigation quite successfully, despite problems in this area which are nothing to do with water. This area has one of the most politically sensitive boundaries in the Middle East running through it. And here at the Jordan River, it's no man's land. On the east bank of the river is Jordan. On the west bank, it's occupied by Israel. But this river does have some use. It's the lowest part of the valley and acts as a drain for all the saline irrigation water in the valley. And it carries this saline water away to the Dead Sea. The Jordan Valley produces over half of the country's agricultural produce, even though it's only about 1% of the area of the country. And this produce is essential to the country's economy. The valley could produce even more food, as there's a lot of land that's still unused but is suitable for agriculture, especially here in the southern end of the valley, but there's not enough water for it. And this may seem a paradox, as there's a lot of water here, but this water's no use at all. It's far too salty, about 8 times more salty than seawater, so it can't be used for agriculture. And nothing can even live in it. It's the Dead Sea. But although it's not practical to extract water from the Dead Sea, there is another physical resource that can be got from it, and that's potash, which is got from the salts of the sea, and it's extracted at the southern shore of it. In addition to potash, phosphates are found at Al-Hassa. This is the country's largest mine. The phosphate occurs in shallow water marine rock in layers a few meters thick of Upper Cretaceous age. But processing requires large amounts of water. The phosphate is taken further south to the Red Sea port of Aqaba. Some is exported, and the rest is treated with ammonia and sulfuric acid to turn it into fertilizer. And this process requires both fresh water and seawater. The fresh water is pumped from the Nubian sandstone aquifer that extends throughout southern Jordan. It's piped 50 kilometers to Aqaba. The fertilizer plant was built here, at Jordan's only seacoast, to provide the vast quantities of seawater needed for cooling. So, although the phosphate resource is a valuable one, it's entirely dependent on water. But for Jordan, there's simply not enough water to go around. The competing needs are not only agriculture and industry, which can be exported, but there's the domestic requirement. The Jordanians themselves need water.